Okay, hello everyone. I'm Dionisis Kakoliris from BugSense, Head of Engineering at BugSense. Glad to be here. Thank you, all of you, for coming here to see the talk. Now, first of all, BugSense is a company that does mobile error reporting, analytics, insights, and you know that kind of stuff that needs to have a big data solution. So, at first glance, you may think that you may use some already made fixed solutions, which will help you just cope with the problem. We tried that. We have tried some early solutions, some established solutions, but there was something missing. So let's get on with it. BugSense, as a company, we are the third biggest mobile SDK in the world, after Google and Flurry. We currently have many devices pinging us all the time, 24/7. We have some requirements that we must stick to. For example, that one, which you may find, OK, that's big, that's small, doesn't matter. So after some time, we just decided to roll our own custom solution, which we call LDB. Now, why would we do that? It's just a matter of having things work the way you want them to, and have it to just be custom tailored for your needs. OK, Monica, thank you. Now, I'm just the guy who is delivering the talk. There are many other people involved in this project, and it's a great effort that began about a year ago. The company right now is cash positive, which means that there are many applications that are using us. Basically, I'm talking about 20,000 plus applications, which means that some of them are hot applications, some of them are cold. But we can provide this service for whatever size one wants. That's why I think that LDB is just, as I told Ville, it's just a success story in Erlang. Without Erlang, a concrete part of LDB would be missing, and we wouldn't be talking right now about the solution. Now, let's have some things first. We see first a picture of how we imagine the data map landscape right now. We have tons of data that are currently in a flat shape. I mean, for example, have this data organized like this, something like that, and so on, which may seem at first sight that it's not really organized. Of course it's not organized, because you can imagine millions of sensors collecting data. Whatever may fit will come. So basically, we have this huge flat field of data. And currently, what we want to do is design something that will be appropriate for organizing, processing, and viewing the data. That's why, initially, we'll just make an assumption that has to do with sociology and city planning. Last slide you saw was all about horizontal scale. But modern cities, if you can imagine them, are also having vertical scale in mind, because that's why they can cooperate better. If you have, for example, a commercial center, if you have, for example, skyscrapers, then you may see that your job is done in a better flow, which means that the idea is workflow here and pipelining. So that's the initial point where LDB is at the picture. Right now, we'll see the whole design idea behind LDB. The whole design idea is having streams, a lot of streams of data pouring in. Each one should have an immutability imprinted into it. And then all of them will clash to something that reminds you of context, of state. That's where destructive updates will take place. But we need to have immutability on this stage. OK, that's our world that provides us with many triggers, many stimulations. And this is where data comes in and pours into our system. Data is very crucial. And what I'm really trying to say here is that the form of data, the data image that will hit you, is at first sight should be indifferent to you. OK? Now, this is the basic design principle. We have many streams of data that are going to hit us. We do processing on each stream in order to have organized it. That's why we also need vertical scaling besides horizontal scaling. Horizontal scaling is that axis. Vertical scale is that axis. We also should keep in mind that the destructive update should be persistent, and this whole system should be fast. Initially, we thought that real-time was not something that we should insist on. But eventually, it emerged that real-time was possible. So, OK, real-time is a feature that we provide. Now, I'd like to pause here for a little while and any of you would like to pose any questions, because from this point on, all the other slides will be clearly obvious to you. Is there any question that you would like to ask from this point? No? I might say something that it's not clear to you, maybe. OK, let's proceed. Now, we're talking about an in-memory complex event processing system that basically is a steam processor that has time series imprinted on it. If you see it as a package, it's very easy to install. You just download the binary or source form. Currently, you don't download that. For us, we're going to open source that. Binary or source form, you just install it, tweak a little bit a configuration file, and then whoosh, it's ready. It's ready to receive your requests. One of the design principles is that we use fine-grained locking on that, which means that all the streams you saw earlier will not have anything to do with big locking on the down layer. So for the destructive updates that I just showed you earlier, we have all these streams pouring in and doing destructive updates on a persistent layer. We use the C language that it's implemented over the port driver of Erlang. Erlang receives all these streams. It has every node ready to accept these processes. It talks with the C layer to the persistent persistence layer we have, and has all this kind of stuff rolling on and on and on. Now, what we'd like to do is have a mentality of describing what you want to do with your data in order to organize it, and have this system to be robust. One thing we have learned about server-side programming during these past years, all of us, is that there is a difference in philosophy if you write client-side programming and server-side programming. Server-side programming is about keeping in mind that it will eventually crash. No matter what, it will eventually crash. It will not work as you designed it in the first place. And it has to have this opportunity to just resurrect with a magic way. Whereas client-side programming is all about having it not to crash, because you don't want your user to see a message box that says, I crashed. While, as I said, on the server side, OK, it will crash, so let it crash and see what's going on. Now, for data processing, as I said previously in Describe Your Data Mentality, we use LISP. It initially began as a DSL, and please forgive me, currently I'm lying to you. It's not right now a DSL. It has evolved to a general purpose scheme implementation. We use the scheme dialect of Lisp. It's, as you may know, functional programming in general is ideal for parallelism, and it's very, very good to think in that way because it provides you with a good layer of abstraction. We also have asynchronous lazy loading of files for data dumps or journaling or whatever the case. They are loaded when needed. We do asynchronous saves on disk. I'm doing this in quotes because we don't mind about the storage that is beside us. We just do asynchronous saves and asynchronous loads, which means that we do merge operations. Merge operations in parallel have to be like a kind of a reducer, which means that the operation that you provide should be associative, commutative, a binary operator with a neutral element. That's why loading and saving can be done in this way, because during loading, with fine-grained locking, we just merge all the data if we have an already established state. While on saving, we just say, OK, what's my current snapshot? Save it. Save the image to disk. All the architecture from the beginning was designed to be modular and extendable because we would like others to build on top of that. And currently, the reason we don't open source it right now is because it's not a general purpose solution. Currently, it suits the BugSense needs. But with the scripting language, the querying language that we use, it should be a general purpose solution with no problem. Now, also, as you may see, I'm mentioning custom reducers and offline processing. Because initially, I told you that we do real-time. Many of our customers need to have complex algorithms. Yesterday, it was very interesting to see the talk by Dr. Lee from Concarix. And I also heard the talk of Mr. Gunaris. Those were pretty good examples of what should your data mean. Because in the end, you just want to distill, you just want to do cherry picking on all this huge amount of data. On the real-time layer, we just do, as I said previously, the organization part. But if you want to dig deeper and deeper and deeper, then it's going to be offline. This is the reason why we don't like solutions like Hadoop. Hadoop is better suited only for offline processing, for our needs and for our traffic. That's why, OK, we do have an offline processing layer, and it just cooperates with the rest of the system by having by writing some custom reducers and custom adapters. For example, you want to extend it with Hadoop, just do it with an adapter. You want to have Python pandas, SymPy, to do some optimizations, discrete optimizations, for example, on your data, just do it. Have an objective function and just drive it. That's what custom reducers are for. And now, this was just in case you thought that there wouldn't be an Erlang-only talk. We just love Erlang because without Erlang, this whole solution wouldn't be possible. It just would be a no-go. We just love how Erlang does node isolation, replication, supervision. Our replication engine is kind of pretty straightforward and pretty simple. And when I first saw that, I said, wow, because my background is not Erlang. My background is different, but it has to do with functional languages and imperative programming, all that kind of stuff. But I haven't used Erlang 2 years ago. And then something came up. A professor of mine at the university Mr. Kostis Agonas, who is very popular in the Erlang community, I saw a talk by him about Erlang and thought about these great features, how they could fit into systems like that. And Erlang, for me, it's going to be a concrete part in every implementation that has to do with big data and that generally has to do with distributed systems that must behave in a concurrent way. So we had all these kind of pieces fit together, and we just found out that the system was fast, robust, and reliable. So I may not say that I trust C, the C language, as much as I trust Erlang. It's not that I'm not a good C programmer or everyone in my team is not a good C programmer. It's just that C is more prone to some tactics that you shouldn't be used to when you do this kind of programming. And sometimes it's a burden to write a whole bunch of things that have to do with that, but eventually we did write parts on it. Now, why did we use Erlang? As I told you in the beginning, this whole thing is just for us a success story of Erlang. We really appreciate how it scales. We couldn't do it in another way. We used other solutions that, from a point on, they just couldn't scale that good. Then, for us, our traffic comes through HTTP. This is OK with Erlang. We have just deployed a Cowboy HTTP server. Everything plays good. Then, the message passing interface, how it handles processes, how it behaves. It's just about the actor model being such a crucial and modern way part of thinking. It just changed for us some perceptions while we were some time ago, I was just doing some database implementation and optimization, and believe me, Erlang has changed the way we perceive things. Now, Nisia is also used in this system, and it's included in Erlang. Erlang has batteries included. We used the port driver. We use Nisia, as I said. We used Cowboy. It's just simple. It's dead simple. The Erlang layer for us is dead simple. We don't do rocket science on Erlang. We had written the replication engine in about 4 days, and the prototype was ready in 2 days. And all of that is in one language. So we really appreciate that, and we're grateful to those people who are making it possible. Now, a little bit part of the architecture of LDB. LDB currently is deployed on BugSense, and we may see that we have it basically, Erlang is on the part of the receiver end, the upper end, shall we say. We have millions and millions of devices constantly hitting us. These requests are received by a bunch of load balancers who will propagate them to the layers below, where Erlang comes into play. Erlang receives this request through HTTP with Cowboy. Then it forwards them to our process DB engine, which is Erlang and C. The C driver written in the Erlang interface. The C driver does all the kind of stuff that had to do with launching the query language in order to process the request, that the query language implements on its backend some primitives for storing data in memory, and all this state, which lives in memory, is replicated. Crucial part. if the system goes down while the image, the DB image, is not written on disk, what should happen? Should I lose the data? You don't have to lose your data because we implement a way of journaling, which means that each request that comes is also stored. And if your DB goes down, because as I said, eventually it will crash. We haven't experienced that much bunch of crashes, but you know, eventually it will happen. Then you just relaunch it. Erlang does an extremely good job at relaunching a process instantly. Then you load asynchronously your data from disk, and you replay the journal logs for those requests that were not in the image. So this way, the replicators have the kind of information that will be propagated to the instance, to the node that goes up, and asynchronously, your data will begin to mix with all the other data that currently is sent. That's why we don't have one node only for receiving some requests, because the receivers are many and they are also mirrored, which means if I go down, then the other one will be up. It will load. It will have other nodes that will mirror him, which will load the data, and you won't even lose the data, the requests that are currently pouring in when you are relaunched, because you have mirrors of that. This is done through the replication engine, which is written in Erlang on its entirety. We also have a part which is called the dance commander. The dance commander has to do all that kind of coordination and the data exchange, because you may want to have, you may want to also have horizontal scale at your system, which means that I have some kind of reducer that will will have all requests, all views of the database pouring into him, and do the reduction in order to provide you with the final result of many nodes. You may wonder why this is crucial. I think it's obvious, because you may not, with so much traffic, one instance may not be enough. The dance commander has parts of it written in Python. So, okay, I told you a lie in the beginning. The system is not only Erlang, C, Lisp, it's also Python in a little bit part of it. Now, the dance commander with the LDB, this whole LDB system, talks with something that resembles JSON. Basically, it's a JSON format, kind of data exchange format. That allows us to implement what Mr. Armstrong said about the middleman. The middleman here is not UBF or something that advanced. It's just JSON. So we only have to write one parser in JSON. It's written in Lisp, and the other end is written in Python. So you may consider the dance commander as the middleman on that. It heavily draws from the compiler implementation principle that you have a back end and a front end. And OK, the back end has to be implemented in several architectures that you may want your compiler to run. The front end should just produce the objective code. And this is the principle we draw from when we implement the dance commander. Now, all this system, which is the core of LDB, along with the dance commander, will serve your views through your browser. When I say a view, I mean when you do a query on that system, which basically has something like no SQL feature. Why I say no SQL? Because it plays in quotes in a similar way. You just hit the database, draw your results, and display them. The display is done by the front-end crew of BugSense, and it's available through a dashboard. So everyone is invited to test the solution by having a project subscribing into the BugSense service. It's free, initially it's free, and you may also see how LDB serves your results. Now, this is a code snippet, just for the sake of generality, which means what? This is written, this is the C part. This is a part of all the C code. It basically is a fine-grained hash implementation for concurrency. Nothing fancy. We have some macros that we do read lock. We do read lock hash bucket. We have a Bloom check. We do a hash lookup. We just insert a scalar value, and we unlock the hash bucket we just locked. And this is all about it. Currently, the C code is about 20,000 lines of code. You see just a little part of it. And I'm telling you that it's not that easy to go on and write on and on and on and on C. That's why we wanted to have only the persistence layer in C, because modern solutions are better on that end. But C provides us with with doing things in a fast way. That's why it was chosen at the first place. Now, the connection between Erlang and LDB. Erlang is the right tool for the job. You just cannot have it in any other way. Initially, we thought we could jump on the JVM wagon. That didn't work out pretty well. We also have good Erlang engineers, a couple of good Erlang engineers that are doing a great job. Our CTO is an Erlang expert himself. Without the actor design pattern, that couldn't be possible. And I want to say that this isn't a finished product. Currently, it's on beta stage. We don't charge for that. You may want to test it. It's free. Now, there was also a high scalability blog about LDB. You can reach it at this address. I'm sorry it didn't fit well because it had a long URL. This is a snippet of Erlang. Everybody knows how easy it is to spawn an Erlang process. It's something that right now is deployed in the field. It's just a little bit of code that we have. You may find that the behavior pattern that Erlang provides you with is it just fits for that kind of stuff, because Erlang for us is a kind of worker. It does just a dirty job of handling all this traffic. Now, as a bonus stage, why did we choose LISP? Generally, to be honest, about 10 years ago, I thought that, oh, LISP, that's not beautiful, I don't like it. Then I initially coded some stuff in LISP. I really liked it. I turned to the dark side, I may say. The LISP part of the LDB system is launched from the C layer. During each request that comes, we don't want to have a shared. We don't want to have shared context with the other launches for the other requests. Each request launches its own LISP interpreter. This is a basic fact for us. Now, we wrote the interpreter ourselves. It's actually trivial to do that. In about 3 days, that was finished by a couple of guys, me and the CTO. The CTO had the prototype in 2 days. Then I came into that. in about 4 or 5 days later, it was finished. The LISP interpreter does the memory handling of this interpreter is done by us. It's pretty easy. We use generational garbage collector in quotes because it's a proactive garbage collector. We just, because the scripts are small, we just say at the end of the script, okay, garbage collect all that stuff and die. And basically, it's pretty straightforward. We haven't seen any latencies that will get us back. And you know, sometimes it's like hitting a wall, and you say that I cannot go faster than that. But eventually, it all played pretty well. We didn't have any problem with that. The next part of our LISP implementation will allow us to have SQL queries, because right now we do it like writing a program in LISP. And OK, it's very easy to write an SQL wrapper for that. LISP provides you with expressive power and abstraction, a level of abstraction that we really wanted, and it was very crucial. Now, because it has heterogeneous multidimensional lists and symbolic expressions, it's just right for data transformation. And when we say that we have tens of data, we mean that we must also do transformations on this data in a pretty quick time window, in a pretty small time window. Now, the prefix notation is also very good for the transformation. It's really awesome to have it there. Immutability as a feature of a functional language is just awesome. Again, it's ideal for the parallel computing model. We thought that without it initially we wouldn't do anything, so it was a factor for us that should really be there. And you see, the only thing that was pretty upsetting us was the question: will somebody volunteer to write LISP programs? Because LISP is not such a fashionable language. Well, it turned out that there wasn't any problem. To every part we talked, to every company we talked, they didn't have problem with that, because at the end we want to provide this system not only as an open source solution, but build some kind of a business around that and do support on this kind of stuff. Now, this is something in LISP. That's a LISP code. Pretty much I can say that I wrote that in one day. This thing does checking in time windows, and it employs some techniques in sets with quantitative operations, which means does something exist? Is it always there? Is it never present? Things like that. You may see reducers, mappers, time warps, and ranges that are pretty expressive. This snippet is here because I just want to show you the expressiveness of the query language that we use. The query language allows us to do very complicated work, and we can have algorithms that are very easily expressed, because sometimes in SQL things are getting really nasty, and we didn't like that. Now, what's next for LDB? For us, hot code swapping does not currently work 100%. We have to elaborate on that more. We have to do better things that will allow us to use it as it was designed. Then we should also implement auxiliary tools for monitoring, support, and configuration, which means that currently you have command line tools and web-based tools that are text. We want to have GUIs built around that, and we want you to have an administrator that will have an easy life monitoring LDB. So the only thing now that, that misses from the cross-platform requirement is the Windows implementation, because we bumped into some problems on the Erlang OTP on the Windows platform and the MinGW compiler. Then, interoperability with other systems is currently not 100% there. We do have some interoperability with, for example, other storage engines or databases, but we would like it to be more general and provide you with an API to do it in a more straightforward and easy way. Now, we also want LDB to have a supporting role in other systems. We want to cooperate with other systems. We want to help and be helped by them. For example, what I was imagining at a point in time was to have Hadoop run in parallel with us. John Blachogiannis, our CTO, did have at one time a Hive adapter for that. It was pretty interesting to do, and currently we are writing some offline algorithms that are using this discipline. Also, one thing that really is, I would really be glad to see is LDB running from a cell phone to a high-performance cluster, a high-performance computing cluster. I know that Erlang has a cell phone implementation, and I would like to see that behave as a node, as an LDB node, because LDB follows the Erlang way of doing things, which means that you have you have a landscape where many dots are connected together. These are the LDB nodes. And it doesn't matter if they are on the same machine, on different machines, or whatever you like. So that would be very interesting, and I think we'll go that way too. Also, what we would like to tell other people who are here and are here for mainly out of curiosity to get an acquaintance with Erlang. We know that currently it's a good time to harness all this potential of modern systems. You have a very great deal of good weapons at your disposal. You should, I think everybody of us should use them and have, you know, distributed systems written, new projects, new ideas. And Erlang is a crucial part, or not only for to just have it as a tool for your implementation, but to know some different discipline than what you were used to until now. I'm just speaking not only for myself, but I think for others here, because when about 20, 25 years ago, when I was a little kid and I started writing programs, that picture changed a lot. Computing has changed a lot since then. Right now I'm 35 years old, and I see the world in a very different perspective. And I see that Erlang and similar solutions are not only the future, but are going to be a prerequisite in future systems. Now, this was something a little bit quick, but you know, our system basically has a design that it's constantly evolving. And that's an aspect that will lead us to open sourcing it. And currently, the reason why we haven't open sourced it yet is because there are some things that are not really there. First of all, we need to do some code refactoring. Okay, that's trivial. It has to do with having your code looking more elegant. We need to do more tests. Currently, the LDB system is deployed for about 5 months on BugSense. We don't consider that to be a 100% good test for that. That's why it's, as I told you before, it's in beta stage. There are some other things that have to be programmed in order to have every feature that we initially planned in there. And we want it to be a more general purpose system. Right now, it fits BugSense needs 100%. But we want it to be a good solution for others. as well. So you see, it's really a kind of stuff that you may find yourself doing incremental updates all the time. OK, I'll open source it tomorrow, but I have to have this in place. Oh, no, I want to have this also, some kind of stuff like that. So we have set a threshold and said that, OK, above that, it really goes to the community to also get feedback and find out some other things that we may have not thought of initially. Right now, LDB is featured on some good blog posts we have seen. We are really trying to promote it as a good solution that will fit many projects out there. You can stay tuned for updates on that on our webpage, which is at BugSense.com. And we also have a blog there. You may find some entries on LDB. Generally, we think that the future is a little down the corner. So when you are trying to see the future, you may think of several perspectives and other viewing angles. One of these viewing angles is this system. We are very interested in hearing from you and listening to other solutions that are beyond the classical, already established ones. We also want to cooperate with these solutions, but we really want to be able to have some innovation on this field. And that's pretty exciting for us. We also want to thank you for hearing us. And now, are there any questions, please?
Well, let's take our speaker first. Thank you.
Thank you very much. OK.
This is great work, Theo. Can you talk a little bit about the type system that you guys have?
Mr. Gunas asks us about the type system we have. On the LISP layer, which is the query language, LISP does not have types.
That's where I was wanting to understand sort of what types are in the database.
Ah,
does that match
yeah,
with
yeah.
the query language, and how does that match with injecting data from Erlang? I don't quite have my head around that.
Very good question. Thank you about that. The type system, how does the type system correlate with all these layers we presented? Now, on the LISP side, you may want to declare some scalar quantities or some set quantities or some maps, some dictionaries. These are mapped to the C layer as primitives between the LISP interpreter and the C layer. The LISP interpreter is coded in C, so it has to know about what type is this, what type is that, as a union in C. This supports, as I previously said, scalar quantities, fixed numbers, in integers basically, real numbers, rational numbers, dictionaries, and sets. And now we are currently in the process of incorporating probabilistic sketches on that. These are not talking to the Erlang layer because the persistence layer is also in C, which means that once C understands what your script is saying, it just stores this in memory to a hash table, and when the time comes, it will store it on storage as a binary file. Erlang does not come in the way. Erlang just handles the request as a string. The string pours in, it gets to the processor, which is written in LISP. The processor does parsing and semantics, and this way you have your types in quotes. But generally, Erlang is not concerned with types in our implementation. When the type is known to the C layer, for us it is done. You may query that, or you may store that, you may process that. That's all the things that go on with the variables that you process. OK. Another question.
So I have one question. So
OK, Ville.
how does it compare to the latest version of Redis that supports Lua scripting. I don't know if you know Redis, the in-memory database that's pretty popular. So the latest version of it supports server-side scripting using Lua, the small scripting language. So I wonder, if you know Redis, can you compare that? How does LDB compare to Redis in this sense?
Yes. Willy asked me about comparing LDB with Redis and the features of Redis. First of all, we did try Redis in prototype implementations, and it didn't do the job in matters of flexibility. Lua is a language, is a scripting language that, okay, you may do a whole lot of things with that, but we really wanted to have the data processing layer with something that resembles an S expression. You see, a symbolic expression. You have the operator and the operands in a dynamic list, in a heterogeneous dynamic list. That wasn't so nice fitted with Redis. Also, we wanted it to scale at our own needs. Redis was great in some aspects, and believe me, we have Redis in this implementation as an auxiliary part because we have pricing plans and our customers need, when we hit us, we need to know at which cluster they will go to. And we do that with Mnesia, and we did have a Redis part before that. And it played really well. It was awesome. But Redis wasn't that good enough for flexibility on the stream processor. And of course, later on, when we tried to write very complex queries as views of the database, it was not so natural to us. We had the Redis prototype ready in about 1 week. It was I wouldn't say it was the best implementation out there. But you know, at some time we hit a wall. And that's when we said, okay, we have done similar things before, we have experience on that. So we started it, and eventually other BugSense engineers joined the project, and now it plays really well. So to finalize that, we didn't regret that. We didn't go the Redis way, or we didn't use Cassandra, or a similar way that we tested in the beginning. Okay with that?
Yeah.
Cool. Okay, sir.
Why not Cassandra?
Why not Cassandra? That may seem a little bit funny to you, but in order to have Cassandra playing really well, you need to have 10 to a dozen nodes. Initially, we thought that, okay, it may seem like an experiment to us, and we want to know, can we really cope with 2 nodes? So, you know, this whole quest wasn't initially to be the biggest thing that BugSense will have. It was to have an auxiliary role. And initially, BugSense did not have that kind of traffic. For example, a year ago, we didn't have that traffic. And we said, we don't want to go that way. Now, as another thing, I told you, I will tell you why it is called LDB. I'm drawing that from Ville's question. Initially, we did write some kind of stuff. Then we said, OK, let's find a name to this. Let's name it. So we really liked the Lambda moniker. OK, Lambda, L, that's good. Sometimes later, I said, OK, guys, why don't we use the S expression name on this? So SEXDB, no, that didn't sound really well. It wasn't commercial. It wouldn't be commercial. After that, we said, no, before that, John Lahoyan, the CTO, said, I started it as Lithy. Lithy is the C layer, which is a kind of wordplay on Mnesia. Lithy in Greek means dormant. Mnesia has to do with amnesia. So yes, it's a guy that has all the drawbacks on him, all the handicaps on him. And then in the end, we said, OK, just keep the L. It fits very well. Stick it there. LDB is the system. Okay, okay. And I just remember that out of the Cassandra question. It was the time when we tested Cassandra. That was the naming of LDB. Anything else?
Yes, we are running out of time, so let's thank
Okay. Thank you very much.